And so first what I'm going to do is go over the upcoming event. Our next talk is the one that's marked in red, April 5th, and that will be our last one of the semester. And this will be Nicholas Coben, who is a instructional support technician in the horticulture division. And we have a great horticulture program here in MJC. It's on the East Campus, it's over in the agriculture section. And so next we'll be talking about the greenhouses they have there and their plant nursery, current plant trends, and what goes into developing new successful plants. So that could be quite interesting. And so that'll be 2 weeks from now, same time, same place here. And then we have MAP, Modesto Area Partners in Science, and they're going to have a really cool talk coming up this Friday called Stomping Through the Marshes. And look at gomphotheres from north central Florida. And gomphotheres are prehistoric elephant-like animals that were in the Florida area back during the last ice age. And same kind of saber-tooth tiger, mastodon, all those fascinating, interesting animals. So that'll be Friday. All next door, starting at 7:30. And she is a professor at San State. So again, I think it's gonna be a really cool talk. The last MAP talk of the year is called Blow Your Mind Marketing. And that is going to be a dear friend of mine named Joe Medeiros, who was the first director of the Great Valley Museum. And he was a professor here too. So he'll be talking about botany, plants. And so yeah, that's gonna be a great talk too, Friday, April 14th, also Sierra Hall at room 132, 7:30. And then finally, the Great Valley Museum, right now they have a really cool exhibit called On Life in the Wild by Thomas Mangelson. You probably haven't heard the name, but you know some of his famous photographs, like the one of the bear in Alaska on a river, it's got its mouth open and looks like a fish is flying into it. That's his photograph, and it's there. And a retrospective of nearly 50 years of photographing wild places. Fascinating, gorgeous exhibit. And their next Friday night science will be Friday, April 7th. And from 7 to 10 p.m. and weather permitting, the house is supposed to be open. Museum will be open. There's usually hands-on activity for the kids to do. So lots of fun. Okay, so I will take this and close this down. Okay. And then I will introduce our speaker. Okay.
Let me put those on.
Okay, there we go. I'll get your stuff out. There you go. Okay, so I need to stand next to you, Dan. I'm gonna get it on film. Okay. It's my pleasure to introduce Dan Che. He received his degree in physics at State University of New York, and then his master's in physics from CSU Fresno. He has been a professor here at MJC since 2015, teaching both physics and astronomy. Prior to that, he taught for 9 years at Hill College in Fresno. And before that, he taught for a couple of years with physics at Fresno State. And before that, he was a teaching assistant also at Fresno State. So his interests include golf, his family, pets. He has 2 dogs, a cat, a turtle, a crested gecko, a corn snake, and a few fish tanks. And I will hand this over to you again.
Thank you. All right, so where's a good spot for me to stand? I'm going to be moving around probably quite a bit, so I feel sorry for you. So this talk was supposed to be from 1800 with William Herschel to the present time, but I have to go back a little bit further. So this talk will be about 350 years of information. And this is one thing about astronomy. Not only do we have the physics, but also the history behind it. And in 1665, and I think everybody knows who this is.
Galileo? No, Newton.
There we go. So Isaac Newton. And this is really the first spectroscopy. And back then, if they had white light, white was a color. But what he did is he used a prism and showed that white lights, when it goes through a prism, the prism acts not to make the different colors, but it breaks apart all the different colors in the white light. And so this is something where if you have a star, we could take that light, we put it through a prism, we can actually break apart all those colors and get information about the objects in space. Now there's also here, mention all my animals. I'm more of a dog person. We got a cat here. Does anybody know the name of the cat of Isaac Newton? These are great Jeopardy questions. So the answer is Spithead. So, okay, so the reason it's named Spithead, this is England, the channel, the English channel between the Isle of Wight and England is called Spithead. So it's an area in England, right? So, by the way, he interrupted these experiments of light when it was dark in the room. So what they needed to do is Isaac Newton, and he gets credit for this. This is too good of a story. He's put in like little cat or dog doors, right? That we use for animals to go inside, outside. So they actually give the credit of inventing the dog and cat door to Isaac Newton. Probably not correct. So once we have white light, right, makes up all the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet. We now have our next astronomer, Sir William Herschel. And in 1781, most famous for discovering Uranus. That's a whole nother lecture right there. And in 1800, he did a very similar experiment to Isaac Newton, but he went a little step further. And he took white lights, right, put it through a prism, separated out the colors. However, the step that he did afterwards is he put thermometers there. So we have red light, and after red, we don't see it because our eyes detect from 400 to 700 nanometers. And we can't detect this, but the thermometers did detect it, and it rose in temperature. And the first name that he gave it in his papers were calorific rays, like calories, heat, energy. However, we did rename those below red to infrared. So this was the first discovery of infrared in the year 1800. And not long after this, Johann Ritter, I believe was his name. He was a scientist that he looked at this part of the spectrum. And they called it chemical rays, energy above violet, which we call ultraviolet. So he started that. So from the 1800s, we now know that there are parts of the electromagnetic spectrum, which I'll talk about in a little bit, that are red light to violet light, which we see, but there's other parts on either part of the spectrum. And in 1870, the fourth Earl of Ross, Lawrence Parsons, by the way, he did not take this. This is an infrared image that we currently have taken with our telescopes. And if you take a look here, right, we see dark red, but we also see these brighter spots where there's craters. So the craters can be some of the hottest spots on the moon. And with a paper, and this is really interesting, you could go to the Royal Society publishing.org, and you can read all the papers that they wrote in the past, and it's really interesting. It's almost like a discussion to you, and that's what they were doing back then with the Royal Society, was they were writing papers back and forth to each other as like a peer review process with the scientific method to try to make discoveries. And a lot of the discoveries about like black body radiation, Wien's law, wasn't around at this date. And so I read the paper, it was really interesting. And he made this with his 3-foot reflector. And by the way, Parson Town, they're very wealthy. The whole town was named after them, right? And he did a calculation, and he went through some ratios and some guesswork to try to figure out what the temperature of the moon would be for its maximum. And he came up with 400 Kelvin, 270 degrees Fahrenheit, which is a pretty good approximation. Now, kind of look through the paper, probably some of it, there was a lot of error. And he probably got lucky for having a temperature that was so close back in 1870. Now, they actually built the largest telescope. And so go back here real quick. So here we have a reflecting telescope that William Herschel and his sister Caroline Herschel built. And they called this the Great 40-foot telescope. It's 40 feet there. The major aperture, the diameter of the mirror, was 48 inches. And this was over like 60 years. This was the largest telescope from like the 1700s to the 1800s. And the third Earl of Ross, I believe his name was William Parsons, he built the largest telescope after that, which was 75 inches. And then that lasted for a long time until, I believe, 1917, when the Hooker telescope was built on the top of Mount Wilson. Who used that telescope? Did you ever hear of Carl Hubble? So the Hubble Space Telescope, but Hubble was the astronomer that found out that galaxies are redshifting. They're moving away from us, which kind of leads us to the end of the talk, which we'll eventually get there. So electromagnetic radiation, I threw out that term, and this is what we're used to, right? We see everything in the room. We see blue, we see red, we see green. But all the other parts of the spectrum, there is no difference. Well, okay, there is a difference. You want to stay away from X-rays and gamma rays, unless you want superpowers. But all these are the same. Electromagnetic radiation has a frequency and it has a wavelength. And so here you can see the only difference between a gamma ray and a radio wave is gamma rays have a small wavelength and a high frequency. Now, which one do you think travels faster through space, gamma rays or radio waves? I didn't give you the right answer option there. They all travel the speed of light. So X-rays, gamma rays, ultraviolet, infrared, they all go through space at the speed of light. Now we're worried about this one right here. And notice how large the spectrum is compared to what we see, right? We see a very narrow band of the spectrum. Infrared has a very large part of the spectrum, and we actually break this up further to near infrared and far infrared, mid infrared. And infrared, well, we are an infrared, we emit infrared from our bodies. It's heat energy. So we could put a plastic bag here, but then we could put an infrared detector, and all of a sudden that bag disappears because we're just detecting the heat from our body. Now, they also use this, right? If you have a criminal that goes out, commits a crime, they can have the helicopters, they have infrared. So even though if they hide in something, we can still see their heat signature. So we glow like a light bulb. So if you're ever attacked, who is this? The predator. The predator can see in the infrared. So how do we avoid the predator? Okay, we got to cover ourselves in mud. By the way, good physics equals boring movies. If you cover yourself in mud like this, they would still be able to see the heat signature from your eyes, and the mud would eventually warm up to your body temperature. But we just ignore a lot of good science in movies. So the electromagnetic spectrum. So all of these parts of the electromagnetic spectrum, they all travel through space at the speed of light. And only really 2 of them we can actually detect from Earth's surface, right? If it comes from a star. We can radio waves. And by the way, do you see like radio waves? They go right through our atmosphere, don't even get absorbed at all. Now, visible light, already the majority of it makes its way through. Some of it gets scattered in the atmosphere. Turbulence can affect it. So we can build telescopes here on Earth, and we get pretty good results. But where are our best telescopes for seeing visible? In space or in the top of mountains, right? That's where we're going to put those telescopes. So the best telescope we have is the Hubble Space Telescope, and it's only a 2-meter telescope. Basically 6'7", well, it's actually 2.4 meters. I always say 2 because it's easier to do math with 2 and 6 and 9, which we do in my basic astronomy course. So we can definitely use ground-based telescopes, but the other parts of the spectrum, our atmosphere really blocks the majority of them. Infrared gets blocked. Also, ultraviolet gets blocked as well. And gamma rays and X-rays, fortunately, those get blocked from space as well by our atmosphere. Now, there are gamma ray detectors on Earth. However, they're not detecting gamma rays. They're detecting the particles that are made with the interaction of gamma rays in our atmosphere. So for infrared, on Earth, we can't really build an infrared telescope. It blocks out the majority of that infrared. So we got to go high. We have to either be in the troposphere or the stratosphere in this region to see this infrared radiation from space. So in the beginning, in 1957, one of the cheapest ways to do this was to build a weather balloon. So they took a weather balloon up into the stratosphere, and it was a 12-inch mirror. And I mean, technology back then, they used film, 35 millimeter movie film. And eventually, so they took the data with this, and eventually it reaches a certain point, the balloon expands, it pops, and they weren't directly communicating with us. So what did they have to do when this balloon popped? Yeah, they had to retrieve it. So they kind of knew what direction was there, and they had parachutes on these things to try to make it land in a certain area. So that was our really first attempt, right, at good infrared imaging. And in 1965, NASA, they said, okay, well, a weather balloon, right, we got to go ahead and we can't really have the detector on board, and like if it crashes, maybe we lose the data. So what they did is they had a Convair 990, and they had a port here, and they actually had the infrared telescope, and they would just take the data during one of the flights. Now, this one ended in 1973 because I had a collision with another airplane in 1973. So they actually had the Airborne Observatory 2, and this was a next step of taking data, right? So we can get up to like 45, 50,000 feet. And this was a project that was one of the most successful ones, Sophia. And in astronomy, we have all these abbreviations, and sometimes in my astronomy class, I joke with the students there that we have a telescope. It's extremely large. So what's the abbreviation for that telescope? The ELT. It's the extremely large telescope. All right. Sophia stands for the Stratospheric Observatory for Infrared Astronomy. And so this was from 2010 to 2022. They actually just stopped this recently. I know some people that worked with this and pretty upset about that too, because it took really good data. And what they have is there's these are the big detectors. The telescope is on the other side. It's a 2.5 meter telescope. And they have all the control panels here. So they just go for a ride, take the data inside. And this was some of our best infrared spectroscopy and data to this point. Now, you can actually go up here, but you got to travel at 50,000 feet. So you need doctor's permission. And this is a great story. I was told by one of the people that kind of leads these missions that one of their participants told their doctor, right, I have to go to the stratosphere, right? And I need your permission. And the doctor was very puzzled. Like, why do you need permission to go to the stratosphere? Las Vegas, the stratosphere? Okay, so they named it, now I think it's called the Strat. But yeah, the doctor didn't know that they actually meant go up 45,000 feet in the sky. And so here for Sophia is the 2.5 meter. It's actually smaller than that. You have to support the telescope in the back. And when you do that, it touches and thermal heat is radiated that way. So really only a certain part of the telescope mirror is used to focus the light to the detector. Now, Sophia can go up about 45,000 feet. And this is in Mauna Kea above the clouds. And this is about 14,000 feet. And this is the IRTF, the Infrared Telescope Facility at the top of Mauna Kea. And in there, there's a 3-meter telescope. And this telescope was built in 1979 and really cannot do as good a job as Sophia because it's lower and more the infrared radiation is blocked. But the good thing is you don't have to fly an airplane every single time. You got the equipment there, and if something goes wrong, you can fix it a lot easier. Now, we really don't have that many land-based infrared telescopes because they have to be at high elevation. Well, we could put one at the top of Mount Everest, but then it would be snowy all the time. You couldn't drive up there, right? So you can't really put a telescope up there. Mauna Kea at 14,000 feet, it has pretty good weather the majority of the year, and it's easily accessible. Now, the only thing here, do you see that in 1979, there was 2 almost identical telescopes that were built at the same exact altitude? The United Kingdom, and where do you think they built the United Kingdom telescope? In Mauna Kea. And people got really upset about this. They're like, why are you building 2 of the same telescope at the same time? Why can't we just do a joint telescope together? But really, those are still today the 2 top infrared telescopes that are built on top of mountains. And this slide kind of shows you the difference between Sophia and Mauna Kea. So this galaxy is just there for image to kind of show you that Mauna Kea is only really good for this near infrared, but it even blocks more. Do you see Sophia can actually see much more of the infrared radiation? So this is still, right, the best way to observe. You have to go higher and go higher. Now, what's the best way to build a telescope? Not in an airplane, not on the ground, but in space. By the way, putting a telescope in space is really expensive. Billions of dollars expensive. So we've had a few since 1970. Got all these. This is the size of the aperture, the main mirror, 0.5, 0.2. These two were 2003, 2009. These really gave us good data, but in different parts of the spectrum, which I'll talk about. So Spitzer was put up in 2003. Now, part of the problem with these telescopes is they got to be in a certain location. They need fuel to move around. And also they use liquid helium to cool off the cameras. Once you run out of liquid helium, you can't just fly to the telescope and fix it. So once they run out of it, what does it turn into? Space junk. I like that. So yeah, there was a event last week where people in California filmed looked like meteorites just going across the sky. And what it ended up being was it was a satellite that was sent up in 2009, decommissioned in 2020, and it was re-entering our atmosphere, breaking up, causing these beautiful lights, which people probably thought were aliens, right? So Spitzer, Lyman Spitzer named after him, and the Herschel telescope named after William Herschel. So 3.5 meters, which is a pretty big space telescope, and Spitzer, those were the two main ones for a while. And now we have the James Webb Space Telescope. And this is where I want to kind of spend the last part of my talk on. And I will mention with the Herschel and the Spitzer telescope, kind of what they were really good at doing compared to what James Webb is designed to do. So in 2021, on Christmas, December 25th, it was launched. After many, many years of delays, finally went out. Now, they were very careful with this because they had a budget of $6 billion, and then $8 billion got increased, and eventually to $10 billion. And if it didn't work, and we sent it out in space, it would be cheaper to build a new one and send it out instead of repairing it like we did with Hubble. So this is Hexagon mirrors, 18 of them. And we launched this in space, and I had to fly into space, get to its location, and then calibrate its mirrors. And it also couldn't just go up like this because it has to go aboard a rocket with a payload. So they hired origami experts to oversee how this thing would unfold in space. And so fortunately it did work. So it's a good story. Also with a telescope, the bigger the eyeball, the better. So we have a 2 meter versus a 6 meter telescope. So 3 times the diameter, area equals pi r squared. 3 times the diameter equals 9 times the viewing, right? So it's 9 times the eyeball in space. So where is it located? Well, we had to fly it to what we call a Lagrangian point, an L2 point. This gets kind of complicated. So we go around the sun, and there's a special point in space which we love to put spacecraft because the Earth blocks the sun, and it's a very stable point. So how many days does it take the Earth to go around the sun? 365.25 days, right? This would be further out. So if Earth wasn't here, how many days would it take for this object to go around the sun? It's further out. Would it take less days or more days? More days, right? Planets that are further from the sun take longer to go around the sun. However, if you have a little bit more gravity, you can shorten that time up. So what happens is Earth will basically work with this object with its gravity and the gravity from the sun, and it becomes a stable point in space, which will follow the Earth. So as the Earth moves, this L2 point will move with Earth. So this point is always between the Earth and the sun. By the way, this is a very popular spot. We are putting tons of satellites here. Oh, and so we got to put a lot of satellites there. We can't put them all right at the center there. So what they do is they orbit around that point. Also, it's easier to, instead of making sure that you're just like sitting at a single point, if you actually can just go around that point, just a little bit of rocket fuel thrusting a little bit around, it's easy to circle a point in space. And so how far away is it? So the moon is about 384,000 kilometers away. The L2 point is about 1.5 million kilometers. So it took a while to get there. That's about 0.01 AUs. We are about 150 million kilometers away from the sun. So we got James Webb to its special point, the L2 point. Oh, and this is just a slide that shows where the James Webb Space Telescope, the majority of the wavelengths that it sees in the infrared. Hubble sees a little bit into the infrared. It went from ultraviolet to a little bit of infrared, but James Webb Space Telescope is primarily an infrared telescope. It can actually see down to 600 nanometers. And Hubble can see a little bit into the infrared, but this is its job, to see into the infrared. Now notice Sophia has a really big wavelength detection, right? So it can see from the near to the far infrared, but it isn't perfect, right? Because it's not out of our atmosphere. So James Webb does a better job than that. Oh, and then we have all these other like Herschel. So Herschel is the far infrared, which I'll talk about in a second, that's the specialty there. And like all these other telescopes here, WISE, was it the Wide Field Infrared Survey Explorer? I don't think anybody heard that, but anybody heard of Neowise? There was a asteroid Neowise. And what they did is they actually decommissioned this and they brought it back online recently. And now it's, instead of WISE, it's Neowise for the near Earth objects. So now it's looking at asteroids. Oh, and we talked about the Spitzer telescope. It ran out of the liquid helium and it can't make its detector cold anymore. So now it's the warm Spitzer, because the camera can't be cooled. So it can only do certain jobs right now. So what we got to do is we have to, first of all, with James Webb, we got it to the point, we got it to the L2. Now we have to align the mirrors. We got to make sure everything's in focus. This was the problem with Hubble. It didn't work. We had to actually go put corrective optics in there. We had to put glasses in Hubble to make it work. So this is one of the first images of the James Webb Space Telescope. What do you think all those are? It's actually the same star. If you count these up, they're 18. How many mirrors are there? 18 mirrors. So the first job was, actually, this is the first job. They had to figure out which star went with each mirror, because they didn't know, like was this star this mirror? Was this star this mirror? So they had to figure that out. And so they mapped all the stars to the mirrors. And then it was a very slow process of just focusing it so we would get one focused image. And eventually they did that. And this was one of the first images that showed, yes, we have it perfectly aligned. Now notice there that whenever you see stars, they have the big spikes on them. We call those diffraction spikes. And the reason for these diffraction spikes is with this telescope, there needs to be a detector in front of the telescope. And you can't just have a floating detector. You need struts or metal rods to hold it in place. Light is a wave, so when it goes through those struts, the waves get diffracted and you get these spikes in images. And this is one thing that I tell students, like, is it space art or is it an actual image? This is the giveaway for a lot of real images, that you actually see the spikes for the stars. Now, not only that, do you see we have all these weird shaped things? What are those? Those are galaxies, right? Oh, and so this image right here kind of shows you how the struts, like how we actually fix the secondary mirror or the detector, will give you different types of diffraction spikes. Now, which one do you think is most similar to this? Yeah, that one right there. Now it's missing the up and down. Also, the shape of the hexagon mirrors will actually give it extra diffraction spikes. So we can actually see that this is what the James Webb Space Telescope looks like here, right? So we have the detector here, right, mounted, right? So we have those three struts. So that's why we get all those spikes. All right, so you helped purchase, thank you for the taxpayer money, you helped purchase the James Webb Space Telescope. So it's part yours. And a lot of those images on NASA, they're free use, right? Because we were the ones that helped fund the projects. And what do people like? Do they like science or do they like pretty pictures? They like pretty pictures, right? So this is, they released these first to you so you would be happy. Stefan's quintet, right? So these are galaxies. And galaxies are going to be merging too. We're going to see a lot of different things with the James Webb Space Telescope, but we do see with other Hubble images and even with small telescopes, we can actually see galaxies going through each other. Now notice here, this is a real image. We got the diffraction spikes of stars. Yep, they took a picture of Neptune, beautiful in the infrared. We can actually see the rings, and all of our gas giants, even Jupiter has rings. And we see some of the moons as well. This was the big one that was released. And this is a whole nother talk, which I really can't get into right here. Do you see those galaxies are bent? We actually call that gravitational lensing. So these galaxies are actually much further back than all the other galaxies. And what happens is, so if you have an object that has mass, light goes by the mass. Light can, well, all objects like our sun warp space around that object. So we call that general relativity. So when light goes near an object, the light can actually bend with space. And just like a magnifying glass, gravity can actually focus things that are much further behind. So this is basically using matter as a magnifying glass for light. Right, so these guys, by the way, so some of these are some of the oldest galaxies we've ever seen. By the way, there are mathematical ways to actually unbend those. Yeah, so we can actually get data from them. Now, this is the other thing. If we take a look at these images, we'll come back to it. What color are a lot of the little tiny ones? They're red. There's a reason for that. So with the James Webb Space Telescope, here's Hubble, and these are the cosmic cliffs. They call this the Carina Nebula. And with Hubble, this is taken in visible light, and James Webb, this is taken in the infrared. Now, a bigger telescope, we get better quality images, right? But also different information. So this here is a star-forming region. So this is a cloud of gas in space. Now, infrared can go through a cloud of gas much easier than visible light. Actually, I think you might be aware of this too. So on a really foggy day, you're driving down the highway. What color do the white headlights appear? What color do they appear to be? Like orange, red. All right, people don't pay attention. So next time you're driving when it's really foggy out, what about those big fire days that we had when we saw the sun in the sky? What color was the sun on those fire days? Bright red. Because the only light that can get through is the red. The red got through the atmosphere and all the other light got scattered more. So red scatters, well, that's why the sky is blue when it's not cloudy out, right? Light comes through, blue scatters, red can go through easier. Infrared can even go through easier, right? So we can actually, with Hubble, there's like stars and information behind it, but we can't see because the cloud is blocking it. But with infrared, do you see parts of the cloud disappear? We actually can see behind the clouds. And notice here, right? The focus is better with the James Webb, so bigger telescope, more focused images. And this gets kind of weird. I'll try to explain it as quickly as I can. Do you see some stars here appear very bright, and then sometimes you can't even see them? This is different parts of the spectrum. So a blue star in the sky emits most of its light in blue, but not a lot in red. A star like our sun gives off its light in yellow, but there are red stars which give off their light in the majority of red. When stars are being born, they actually are in the infrared, and so that's where they give off their light. So what we can start to see in some of these images are maybe stars that are being born, and this is what this is, a stellar nursery. Yeah, so it gets really complicated though. Like some of these stars, the reason why this star is bright here and really not observable there, it has a lot more infrared light than it does here. You're basically looking at visible light versus infrared. There's a story, there's a difference between that information. So two main jobs. This is not like, we have telescopes, infrared telescopes that can do a good job with this, looking through the cosmic dust. The near infrared really helps us with two things, and this is what James Webb was designed to do. Number one, we like Earth-like planets. We want to find aliens, right? So our atmosphere blocks a lot of infrared, right? If an alien had a James Webb Space Telescope and looked at Earth, it would see, well, we absorb certain parts of the radiation, right? But they would see that we're missing parts of that radiation. So if this is a planet like Earth going around a star, the starlight would go through the atmosphere. However, there would be parts that wouldn't make it through the atmosphere. It would basically soak up some of that energy. And if we take a look at the data from it, we would see that there would be water in the atmosphere, methane in the atmosphere, ozone, water that are soaking up some of that infrared radiation. And so we want to try to find planets that have an atmosphere like us, right? So greenhouse gases, carbon dioxide, methane, right? All these things are carbon, hydrogen, oxygen, it's different combinations of these. So this is what we're looking for. And this is one of the James Webb's first objects. Well, they didn't do an Earth-like one because that's really hard. You've got to make sure the equipment's calibrated. So they did a hot gas giant, something bigger than Jupiter. And they did the spectroscopy, and they found out that there was a lot of water in the atmosphere of the planet. Okay, it's hard enough to do spectroscopy from a star, right? So what we're doing here is we're waiting for a planet to go in front of the star, the light to go through the atmosphere, and basically figure out what light is being absorbed by that atmosphere. That's above my pay grade. Some of this stuff gets very, very complicated. So we're going to try to find Earth-like planets with atmospheres, goal number 1 of James Webb, or not as important as this one, both equally important. This is the one that's giving us a lot of questions now as scientists. We can see, and this is kind of weird, when you look at a star, you're looking at the past. So if a star is 100 light years away, how long did it take that light to get to us? 100 years. You're always looking back in the past. If a galaxy is 7 billion light years away, how long ago did that light come from that galaxy? 7 billion years ago. Telescopes are time traveling machines, the closest thing we can do. James Webb Space Telescope, we can see until here with Hubble Space Telescope or big telescopes. However, the further back you go, I'll talk about a redshift, the galaxies that are farther away from us are moving quicker away from us. So basically the universe is getting bigger and bigger. So we have something called the dark zone. And actually it's called the dark zone because light isn't available to see here. But guess what is available to see there? Infrared. So if we take a look at these old galaxies, we see these old galaxies are red. And the reason for that, okay, first of all, if you see a red star and a blue star in the sky, the red star is red because it's red. The blue star is blue because it's blue. They're not shifting enough to actually change color, okay? However, things that are really far away from us, they can move so fast away from us, not only can they change the color of the galaxy to red, but some of these would be invisible to Hubble because this is an infrared image. So they're not only red shifting to red, they're red shifting to infrared. So basically the light waves are being stretched out. Remember we saw the electromagnetic spectrum, right? Everything's the same. They're basically being stretched out so much that their wavelengths are way above 700 nanometers. And so we call this a redshift. This is called the Doppler effect, right? So if you ever get pulled over by a police car, right? You hear the siren, you hear the higher frequency. And what are you hoping? Yeah, the police officer goes past you, and then all of a sudden you hear that relief, that lower frequency. Now with lights, we can't hear it. However, the waves still get expanded or compressed if the object is moving away or towards us. All right, so most galaxies, the universe is expanding. They're going to be redshifting. There's one galaxy that is blue shifting towards us. That's Andromeda, our sister galaxy. And eventually that galaxy will hit and collide with the Milky Way. Don't worry, it will be way gone before that. Now, this is kind of where we are right now. We wanted to peer back here, and we had models about how galaxies would form, right? So after the Big Bang, we would expect, before we would have big galaxies, that maybe we would see like smaller galaxies or smaller structures, and those things kind of build up to give us galaxies. But what we found is the oldest galaxies are supermassive and developed much earlier than we thought. And so these little dots are galaxies that the James Webb, the oldest galaxies to date. And we are puzzled by why they're so big and how they developed so early after the Big Bang. So we have questions, and I don't have answers to this. And so galaxy evolution, these models have to change to take this into consideration. So this is what we are, I say we, I have nothing to do with this. I do astronomy. I am not doing any of the actual theories with all this, but astronomers are now looking at early models and maybe trying to change some things and come up with some solutions for this. Now, a couple of things which was mentioned at the beginning. Has anybody here been at Science Night before at the Great Value Museum? All right, so the first Friday of every month, for most months, I think January we don't do it, and May because of graduation, but we will have it on April 7th, 7 to 10 p.m. We have telescopes. Well, we have our own observatory. We have a 28-inch telescope, and you get to look at that with an eyepiece, and we'll have an object like Orion's Nebula, Mars is out, a couple of other objects. And we also have our astronomy club, which has, we usually take out about 6 12-inch Dobsonian telescopes. So they are about this tall, about this wide, 12-inch mirror to look at objects as well. And so these are open to the public. We have telescope viewing 7 to 10 with the time change. Doesn't get dark till like 7:30, 8 o'clock. So people get upset when they go there, right? And also they get upset because if it was today with telescope night, we like to look at clouds in space. The clouds on Earth do not help us. But if you've never been to these events, they're free, open to the public, and we stay out there from 7 to 10 p.m.
You want to add, the planetarium shows are not free.
Yeah, planetarium shows are $1 for students and $5 for the public. I think like $4 for kids, and entrance to the Great Value Museum. But the telescope viewing, completely free.
You have a question on the Sophia.
Yes.
Why do they get continuous money? As you were saying.
It's funding, yes. And one of the things here, if you take a look at this slide here that I had with Sophia, this quote right here. One of these programs I'm working on right now, this is a slide. And if you read the bottom here, that's a cry for, we want money, we want this to continue. Sophia did a pretty amazing job. So
was Sophia under NASA?
yes, Sophia was NASA. Any other questions?
that slide where you had like six dots, like the bright dots, that were the really, really old red galaxies or whatever. So are those were all different ones, 6 different ones?
Yes.
And then, if it's looking like so far back, it's looking in a limited part of the sky, right? You can't look all over the place and also look so far. Is that am I right?
So a couple of different things that we can do. We can look in a bright part of the sky. And if we have like gravitational lensing where other bigger matter type objects will focus the light of the objects behind it. Some of this stuff is we try to look at a dark part of the sky and we just take longer images, so longer time exposures to try to bring out those faint objects. Now, with Hubble, like to take an image like this, when they did the deep fields, I think they were like 30-hour images, and James Webb can do that in like an hour or two.
So then it can rotate, they can program it and make it point in a totally different direction.
Yeah, yes. So basically as the Earth, right? So it just once it's back at the Earth, right? So it's at that L2 point. So basically its back is at the sun. It actually has like gold foil in the back to reflect the energy and not allow it to get to the instrumentation. And it does kind of use Earth as kind of a little bit of a light shield as well.
Oh, it's blinking, we're looking just away from the sun there. We don't
Yes.
see anything that's on the other side of the universe, on the other side of us.
Well, the thing is as Earth goes around the sun, we'll be able to get all parts of it. Yep. Any other questions?
And there's some new telescopes that are going to be launched in the near future.
I'm not, yeah, so I don't really keep up with a lot of the ones that are being launched because of the funding and if they actually get to the point where they make it. So I was joking around with the extremely large telescope, right? That was supposed to be built by 2024. Now it's going to be like 2030. What they're doing now with like visible telescopes is we have something called adaptive optics where they shoot a laser into space and it can actually see how the atmosphere is reacting to that light. And then in real time, we can actually use that information with adjustable mirrors to cancel out that turbulence. So basically, we can make the atmosphere disappear with adaptive optics. And so that is a big thing right now. And we really want to push that forward because this is crazy. It's cheaper to build a 40-meter telescope on Earth than put a 2-meter telescope into space. And so if adaptive optics really works well, it's going to be better than Hubble on Earth. But Hubble does a pretty good job being 2.5 meters.
So if light takes so long to travel to us, does that mean that like some of the stuff we're studying is not even there?
Yes, yes. So, or compare will be completely different. Now, so the question was, we're looking back in the past, right? So some of the stuff may not be there. Now, all the stars that you see, they're going to be there. Because if we see a star that's 1,000 light years away, what is 1,000 years for a star? Yes, okay, that's like us. We're still here. Okay, so that's good, right? Same thing with the stars that you see in the sky. Now, the one things that like will appear to be different would be like the galaxies, right? That are hundreds of millions of years ago. even like some of those stars in the galaxy that we can see, they might not be there. We actually see stars blow up in those galaxies with supernova, right? So, but that happened a long time ago, so those stars are no longer there. So, yeah, it's a strange thing with astronomy that we see a story around us, right? We see the past, and we're trying to reconstruct the past to give us models to show us like what's going on currently with the universe of getting bigger and expanding. So, yeah, I tell my students with astronomy, don't worry, we just got to talk about 13.5 billion years of information in this course. And the only thing we're studying is everything besides Earth, which is quite a bit. Yes.
You talked about the L2 point.
Yes.
Are there any other points like that may be further out?
No. So
That's unique by itself.
that yeah. So I guess like, I mean so this is like the three body problem. We have to calculate these points. Those are specifically for Earth. There would be maybe one for Jupiter, Mars, right? I guess we could use those. I mean, it's a much longer trip out there. It would take more fuel to get to those locations, and actually transmitting the information back would be an issue as well. Yeah, time delay. And also with Mars, it would actually, I'm just going off like my brain here, just like kind of picturing it would be closer to Mars because it would be less massive. So the L2 point would be on the other side of Mars, but it also would have interference of sending that data back during certain times of the year as well. And we wouldn't be able to see Mars, right? It would be complicated. But yeah, there's like an L1 point, which is before, and then we have these like other points that are on the sides. The L2 just works out really well for observing for astronomy.
So James Webb is supposed to see as far back as the dark zone
Yeah, so
before the cosmic mass that everything was just confused.
yeah, so like millions of years, like after the Big Bang, we already detected galaxies.
But not as far back, not through. Does the infrared, could it see through the cosmic microwave back then?
This is weird. We get that information from microwave and actually radio telescopes. So they actually say, a lot of young people have no idea what I'm talking about, but remember we had those TVs with the rabbit ear antennas and you had the static. A little bit of that information was the cosmic background radiation left over.
So we've already seen closer to the Big Bang time.
Yes, yes. Yeah, we actually we can map out the background radiation. Right, and so, and this is the thing, like radio waves can easily go through like space and atmosphere. That's why we detected it first on Earth, right? Because radio waves and microwaves are close, but parts of that spectrum could go through. And we have observed this. This was the part that James Webb.
And that there's that orange red space down closer to the Big Bang. How do we know where the cosmic background, cosmic microwave background ended? I mean, you've got the sections based on the time.
This is the problem. We're giving you a model. Oh, and you're not going to like this answer. This is the cosmological principle. I know in your head, you're saying, okay, there's a center and everything comes out from the center. Cosmological principle says there are no special positions in space. So basically this the background radiation just everywhere around us, right? But this is the like going back even further than that, that involves a lot of models and me talking about high energy particle physics and like the standard model, which I don't think I could get into right now.
But it says 200 to 500,000 years ago.
Mhm. So basically,
Well, I'm wondering how beginning point would be reached.
oh, to go back,
How do we know it started 200, 500,000 years from the time of the bang, right?
yeah, so there are different models. So this is the Big Bang, right? That is a theory of a model. There are different models as well. But this is the most accepted in astronomy, right? So the Big Bang theory, right? How the universe started from a singularity, right? Going outwards. We see this, and what we do is we can actually see the energy here, kind of like how matter was like originally kind of put out there. And a lot of like from here going backwards involves getting to this point.
So I know there's an alternate theory, at least one, that there was
There's just not one.
Big Bang.
Yeah, so there's different like different models too of like how the universe expands, like how the death of the universe is going to happen. So there's like a model that says the universe is basically just going to keep on getting bigger, bigger, bigger. Maybe a model would be the universe just rips itself apart. There's a universe that the universe will just go on forever with what we call entropy. And basically the universe will become so disorganized that nothing will be left.
That describes my process.
Yeah, so
Well, there's also the theory too, where
the big crunch.
where it goes back.
Yep.
And
Yeah.
then start again.
Yep.
Okay,
So
well,
which iteration we're in?
Yep. So we,
question, you can come up and.
yeah, if you can come up here too. Any of my students, if you want to come up here, sign my notebook. You don't have to write the paper. People are excited.